Chromatography is the separation of a mixture or two or more compounds or ions by distribution between two different phases. One is called the stationary phase. It's stationary, doesn't move. And the other is called the mobile phase, and it does move. And the basic principles depend on the different solubilities or adsorptivities of the substance to be separated relative to the stationary phase and the mobile phases. So looking down below here, we see a TLC plate, thin layer chromatography. We see a column for column chromatography, and this is a GC, or a gas chromatography instrument. And we're going to talk about all three of those. The types of chromatography that are routinely used, again, are solid-liquid chromatography. Now, solid-liquid chromatography, the stationary phase is solid and the mobile phase is a liquid. Common examples of this are column, so column chromatography, TLC, or thin layer chromatography, and paper chromatography. Now, TLC is routinely used to determine purity, monitor reaction progress, and also to identify an unknown. The other types of chromatography that are commonly used is liquid-liquid chromatography. That's also known as HPLC, high performance liquid chromatography, and gas-liquid chromatography, which the stationary phase is a liquid and the mobile phase is a gas. So this is gas chromatography. Now, in thin layer chromatography, the stationary phase is a compound or substance that's been coated onto a plastic microscope slide usually. Now, if we put in this TLC plate into a beaker and place a watch glass over the top of it and put water, for example, in it, now the water will be pulled up, or the solvent, the mobile phase, is pulled up that TLC plate. So it moves up. So let's look at an example here. What if we had a mixture of two compounds? And let's make it simple. A is this red dot. We'll say it's nonpolar. And B is this blue dot. We'll call it the polar compound. So what we'll do is we'll take that TLC plate and we're going to lightly mark the origin, or the base of it, with a pencil. And you want to get a smooth edge on your pencil. So if you have a mechanical pencil, you want to try to smooth it out on a piece of paper before you write across this, because the coating can be this kind of delicate, chalky material that if you press too hard, it can etch away a small canyon. And if you press hard enough, it can go all the way down and etch off all of the stationary phase down all the way to the little piece of plastic on the microscope slide. We're going to spot our sample, and we're going to use a TLC capillary tube. They're like melting point capillary tubes, except they're open on both ends. So you put a little spot on there. So this spot is going to be purple. It's the overlap of red and blue. And the type of stationary phases that are common to use in organic chemistry lab, they're polar stationary phases, and they're usually some form of silica or some form of alumina. But nonetheless, I want you to view these things as being polar. And because of that, polar solutes are going to bind more strongly, or be attracted to more strongly, the polar stationary phase as compared to things that are less polar, right? So like dissolves like. They like compounds similar intermolecular forces, they're attracted to each other, right? So there is another type of chromatography out there, and that is called reverse phase. So typically what we're going to see is a polar stationary phase, and then we use a non-polar solvent as our mobile phase. There's a type of chromatography called reverse phase chromatography, and in that type of chromatography we switch the polarity of the stationary phase and the mobile phase. So the stationary phase becomes non-polar and the mobile phase is a polar solvent. So this is used in TLC, but it's also used in column chromatography. Now back to our example. So let's take our TLC plate and let's place it into an elution chamber, here a beaker with a watch glass over the top of it, and let's use hexane. Hexane is a nonpolar solvent. So Remember, our stationary phase is polar, right? And we have two components, one that's polar and one that's non-polar in our little spot there. Now, as we allow that solvent to move up the TLC plate, we start seeing a separation here. So as it moves up, the compounds, those two dots, the two components of our mixture, start to separate. Remember, the blue dot is more polar, so it's adhering to the stationary phase stronger because they're attracted to each other. The mobile phase is nonpolar, and the red dot there is our nonpolar compound. So it's getting pulled off of the stationary phase and moving up with the solvent. As that solvent moves up towards the top, our spots separate from each other. Now, in the end, we see that spot A, that adheres to that polar stationary phase less. It stays in the nonpolar mobile phase more, and because of that, it moves faster. It moves up the TLC plate faster. Whereas B adheres to the polar stationary phase more, and it's lagged behind, it's being pulled behind, right? So it just moves a little bit less. So we can separate compounds like this. Now, if we look microscopically at kind of what's happening here, right? Here is like a close-up view of our TLC plate. We have this solid polar stationary phase, so that's the coating. This is like a side view, right? And imagine there's a little bump here with your compound A and B all kind of piled on here on your origin. And they're just sitting on there right now. And we're going to take our plate and we're going to put it into our solvent, which was hexane. Now, as hexane starts to move up the TLC plate, the compounds that are nonpolar are going to kind of migrate into that solution a little bit. So A is the nonpolar solute that we're talking about. It's going to move over. B hangs out and sticks behind. It still moves a little bit as we kind of progress up our TLC plate with the solvent, but it doesn't move quite as fast as A does, as we saw in that last example. So what we're going to do after those spots get up close to the top is we're going to watch this solvent line. This is called the solvent front. And when it gets close to the top, we're going to have to pull it out. So we're going to take it out. We'll use a pair of tweezers to do that. And then we're going to mark right here the very top of this thing. And we're going to do that lightly with a pencil. So we can't use a pen on these because pens are made of organic, the ink is made of organic compounds, and they start to separate on the TLC plate. And then we're going to allow this to dry upright in a fume hood or in a ventilated area in the lab. Now, once you have that TLC plate all dry, you're going to take some measurements. So we are going to measure from our origin all the way up to the solvent front. Here it's 10 centimeters. And we'll measure from the origin up to spot number 1, which is 1.5 centimeters. And again, from the origin up to the second spot, the nonpolar spot up there at the top, 8.2 centimeters. And we'll calculate something called the RF factor. That's equal to the distance that the spot traveled. So 8.2 centimeters divided by the distance that the solvent traveled, which is 10. So 8.2 divided by 10 gives us 0.82. And we get 0.15 for our blue spot there. Now in this example, these spots started off as having color. So sometimes spots don't have colors. There's compounds that are colorless, right? So we have to visualize them. So sometimes you run TLC, and when you're done, the plate just doesn't look like there's anything on them. So how do we visualize our spots? Well, often we use something called a UV-vis chamber. And what we use is a type of TLC plate that has a natural fluorescence. So it's coated with a fluorescence indicator. And that indicator glows under UV light. So you come over and you put your eyes on this end right here, and you turn the lamp on. There's a little hole on the other end where you can put your sample in. You visualize and you take a look, and the whole plate looks like this. And the dark spots are simply where the compound is masking the natural fluorescence of the TLC plate's background. So that's a type of plate that we use when we do this experiment. Other times, sometimes you can take a little bit of iodine crystals and you can take the TLC plate and you put them in a jar. And there are some functional groups that react with iodine and they form brown spots. There are other things too, like proteins. Proteins will react with ninhydrin. So you can spray ninhydrin on your TLC plate or whatever you're analyzing. You can heat it up a little bit and then the spots will turn purple. Now, There are some factors at play here for thin layer chromatography. In fact, chromatography in general, there's some solute-solvent interactions. So more polar solvents tend to remove polar solutes from a polar stationary phase, right? So this is the elution sequence for compounds. And really, we're starting off here with things that are pretty nonpolar, going up to more polar compounds. So these more polar compounds down here at the bottom, these are slower to elute or to move on a TLC plate, and they require a solvent with some type of polar character to get pulled off. So we have a list here of different solvents. Starting at the top, you have petroleum ether, cyclohexane, toluene, working our way down to alcohols, ethanol, methanol, water, and acetic acid. Right, so we might require, for example, something like methanol or some even mixture, maybe methanol and water, right? Or methylene chloride and toluene or hexanes, right? That falls down here in the petroleum ether cyclohexane area to help pull off polar solutes from our stationary phase. Now, the goal is, again, to choose a solvent that allows for solutes to be separated from each other. So in this example, we have a solvent that's two polar. All of the spots have moved to the top of the TLC plate. Here, our solvent is two nonpolar. Spots are hanging out down at the bottom. So we find the right solvent. So we can look at that table, or we can do, mix some solvents and try different percentages to try to get some nice RF values. Typically speaking, in organic chemistry lab, solvents are given to you to use, so you don't have to figure this out on your own.